Welcome back, everyone. The next topic is going to deal with enthalpy. And enthalpy is the amount of heat that is transferred to a reaction. And so what we're going to look at is we're going to look at changes in enthalpy based on stoichiometry, which we all know and love. And so two things you need to remember. Delta H is what we used to signify enthalpy. Delta H is positive. Then that means that it is an endothermic reaction. That means that we've taken energy into the system, and we've talked about this in the last topic. When you take energy into the system, that means that energy is going to become positive, okay? So whenever we have a delta H that's positive, that also means it's an endothermic reaction. So on the opposite, if delta H is negative, then we know that this is an exothermic reaction and that energy is going to be given off, okay? Not going into the system, but being given off by the system. All right. So whenever you see these equations, a lot of the times on this worksheet, what you'll see is a negative number for delta H value. That's okay. You can have a negative delta H value. You just have to remember that means that the energy is being given off by the system, not being taken in by the system. Okay. So do keep that in mind. I'm going to go ahead and run through some of the problems on this worksheet with you just to give you some examples. And so we'll start with number one. For number one, the question says, how much heat will be released when 6.44 grams of sulfur reacts with excess O2 according to the following equation? And then it gives you the equation. It says 2S plus 3O2 yields 2SO3. And it says that the change in enthalpy is going to be a negative 791.4 kilojoules. Okay. So keep that in mind. This is going to be an exothermic reaction. Not that you need to know that for any particular reason to answer this problem, but just that it is. You're giving off heat. And if you're starting out with 6.4 grams of sulfur, 6.44 grams of sulfur is what they want you to know. What you have to do for these problems, you have to convert grams to moles. And then you are going to do a mole to energy ratio in order to figure out how much energy you have for that particular equation, okay, or for that particular amount of sulfur. So if we start out with 6.4 grams of sulfur, this is how much energy that's going to allow us to create and give off, okay? And so with 6.44 grams of sulfur, first thing we have to do is change from grams to moles. We all know how to do a gram to mole conversion. For every 1 mole of sulfur, according to the periodic table, that's 32.6 or 32.06 grams of sulfur. Okay, that'll get rid of that unit. And then the next step, if we go from moles of sulfur to energy, well, what we need to do is we need to figure out how many moles we have by looking at the coefficient in the periodic table, or from the equation. Our coefficient here is a 2, and so for every 2 moles of sulfur that we have in this problem, we produce negative 791.4 kilojoules of energy. That's it. That's all you're doing. You're figuring out, if you start out with a certain mass, how much energy you can create given that mass of one of our particular products or reactants, okay? So when we do the math, again, you would multiply across the top, divide across the bottom, and if I did this, I could actually produce a negative 79.485 kilojoules of energy. Now the reason this is negative is because we are giving off the energy. So we're producing it, not taking it in. So giving off energy. So keep that in mind. All right. Problem number 2. I'm going to do that one for you. It looks very similar. Problem number 2. It says how much heat will be released when 4.72 grams of carbon reacts with excess oxygen according to the following equation. Keep in mind, when it says excess oxygen, what that means is that you don't have to do a limiting reactant problem. Remember when we did limiting reactants, because we start out with so much of this and so much of that, we had to see how much we could make given the 2 reactants. They're telling you you have more than enough oxygen. So what's going to be your limiting reactant is the amount that they give you in this problem. And so the reaction is carbon plus O2 yields CO2. And that's going to give us a change in energy, or our enthalpy change, of negative 393.5 kilojoules. Again, this means we're giving off the energy because it's negative. It's telling us that we're starting out with 4.72 grams of carbon. First thing we do is write down what we know, 4.72 grams carbon. For every 1 mole of carbon, that's going to be 12.01 grams of carbon according to the periodic table. And then we look at our coefficient here. Our coefficient is a 1. So for every 1 mole of carbon, we can produce a negative 393.5 kilojoules. We go ahead and do this math. You should end up with a negative 154.65 kilojoules of energy that is going to be given off from this system. Okay, so if I start out with 4.72 grams of carbon, that's the most change of enthalpy that I could make. All right, now I'm not going to do problems 3, 4, and 6. Problems 3, 4, and 6. All of those problems on this worksheet are done the exact same way. You're given a mass, and you're going to go ahead and convert it, okay, the exact same way. You figure out gram to mole conversion, figure out how many moles you have in your equation, and then solve the problem. Okay, so I'm going to move on to number 5, solve that one for you, and then do 7 and 8 as well. All right, number 5. Number 5 says, what mass of propane, C3H8, must be burned in order to produce 76,000 kilojoules of energy? All right, so this one we actually have to work in the opposite direction of the ones we just did. Instead of giving us mass, they want us to find the mass. All right, so we start out, okay, knowing that we want to produce 76,000 kilojoules of energy. Okay. However, according to our problem here, we can only produce a negative, okay, 2200 kilojoules of energy. Now, we are producing 76,000 kilojoules of energy. So keep this in mind. Because we're producing it, we are going to make this a negative as well. Okay, because when you do the math in the end, you would end up with a negative mass number, which isn't going to, be possible. So we have to make sure that we realize, because it's being produced, that 76,000 kilojoules is also negative. All right, and so we need to look at our equation. Our equation says C3H8 plus 5O2 yields 3CO2 plus 4H2O. You need to do your ratio here, just like you did up here. You said there was 1 mole of carbon for every so much kilojoules of energy. Here, we're going to do the same thing. We also only have 1 mole of C3H8 in our equation because there's no coefficient in front of our C3H8. All right, so that gets rid of our units of kilojoules. And then we need to change to grams. So for every 1 mole of C3H8, if I do the math on that, if I find the mass of C3H8, you guys know all how to do this. I'm not going to spend time working that out, so forth and so on. That's going to give you 44.11 grams of C3H8. Okay. So now you do the math, because that's going to leave you with how much mass you could produce if you start out originally with 76,000 kilojoules being made. Okay, so the mass that you would need to have of this propane reactant would be 1,523.8 grams of propane. Okay, so you're just working backwards is all you're doing. Okay, number 7, same thing. Remember number 6, we're going from mass to energy, so do it like problems 1 and 2. For number 7, they're asking what mass of iron must react to produce 36,000 kilojoules of energy. And the equation says 3Fe plus 2O2 is going to yield Fe3O4. And the delta H of that reaction is going to be a negative 1120 kilojoules. Okay, so again, start out with what we know from the problem. 3,600 kilojoules. And it says produce. All right, so if it's saying we produce it, not take it in, that's going to be a negative amount. All right. First thing we have to do is we have to do a mole to kilojoule ratio here. And so how many moles of iron do I have in my problem? Well, I have 3 moles of iron in my problem. And that 3 moles of iron would allow me to produce normally 1,120 kilojoules of energy. Okay. The next step then is a mole to gram conversion. So for every 1 mole of iron, according to the periodic table, iron is 55.845 grams. And that is going to give me that I am going to require 538.5 grams of iron in order to produce this original negative 3,600 kilojoules of energy. Okay. And the last problem, number 8. Number 8 is extremely easy. Okay, you're going to work the problem just like you did with number 1, number 2, because you're trying to figure out how much heat. The problem is that they're giving you 2 masses to start with instead of 1. So what this is this is going to be a limiting reactant problem. You have to figure out which one limits the amount of energy you can produce. So if I take a look at this problem, it is wanting to see how much heat energy will be released when 12 grams of hydrogen reacts with 76 grams of oxygen according to the following equation. And again, it tells you one reactant will run out before the reaction, before the other one. So the reaction will stop when that one runs out. And so the equation is 2H2 plus O2 yields 2H2O, and my delta H is going to be a negative 571.6 kilojoules. All right, so I have to do 2 problems. One for my hydrogen, which is 12 grams, and one for the oxygen, which was 76 grams. Okay, I'm going to go ahead and start with my hydrogen one. For my hydrogen one, I start out with 12.0 grams of H2. Okay. I'm going to have for every 1 mole of H2, that's 2.02 grams. Okay, keep that in mind. It's H2, not just H. In this problem, I have 2 moles of H2. And every 2 moles of H2 that I have produces a negative 571.6 kilojoules. That gives me a total of a negative 1,697.82 kilojoules. All right. The second step, 76 grams of O2. Okay. Well, for every 1 mole of O2, I would have 32 grams of O2, so 2 times 16. And then in this problem, I only have 1 mole of oxygen. Okay. And in that 1 mole of oxygen, I will again produce 571.6 kilojoules of energy. When I go ahead and do this math, I end up with negative 1,357.55 kilojoules. All right, so how much energy can I produce? How much heat will be released? I can only release as much as my least amount will allow me. And so the least amount the most I can actually produce is the one that limits it. And that would be this one, okay, the negative 1,357. All right, if you have any questions, please email me, but I've basically done all the problems on this worksheet or showed you examples of all the types of problems. So hopefully you can do these on your own. Okay, I'll talk to you guys next time.